Now we're going to talk about the idea of balancing redox reactions, which ends up it's a little more complicated than balancing reactions that we've learned about previously. So if we look at the reaction copper solid plus silver 1 aqueous, so reacts to become copper 2 aqueous and silver solid. So copper metal reacting with silver ions to make copper ions and silver metal. So on face, we would think, this looks pretty balanced. I got 1 copper on each side, I got 1 silver on each side. But the other thing that we need to consider, the other thing that we need to look at is going to be the charge on each side. If we look at my reactants, I have a neutral copper atom, and then I have a +1 silver atom. Whereas on the products, I have a +2 copper and a neutral silver. All right? Those differing charges imply that there are different numbers of electrons. This reaction, as written, has 1 fewer electron on the product side than on the reactant side. That is not balanced. Normally, when we think about balancing, it's all about atom types, but we generally kind of are assuming in those cases that all the electrons are sticking with. In these redox reactions, electrons are going to move between atoms, so we need to account for how those electrons flow in a balanced and conserved way. You can't just destroy electrons, and conversely, electrons don't just come out of nothingness. So the primary method that we're going to introduce with balancing that will hold throughout this chapter is the idea of splitting your overall reaction, your overall redox, into half reactions that are based around oxidation and reduction. This is why we define reactions in this way, as with these two processes, because we're going to think about the oxidation half, where you're losing electrons, and the reduction half, where you're gaining electrons. And so basically we split these based off the atom types, right? Because like the silver is still the silver nucleus is still going to be silver. All that's changing is the electrons around it. And so we keep those the same, and then we balance each of those based on the number of electrons to balance the charge. We know that electrons are just being kind of transferred in the reaction. We're not losing or gaining electrons. But by breaking it into an oxidation, we can see about loss of electrons where the electron is on the product side. We can think about reduction where the electron is on the reactant side to balance, right? And basically how we balance, we can see this is neutral. If I have +2, I need to have -2 on that side as well. And so this idea of taking an overall redox and splitting it into the two halves is going to be fundamental to how we move through electrochemistry. It's going to be coming up again and again throughout this chapter. So if we take those half reactions that we just came up with and we combine them back together, we can see that we end up with an electron in the reaction, right? This 1 cancels out one of those 2, leaving you with 1 left over. And that's a problem. This is kind of, we said before that the charge was imbalanced, and this is really showing it. The reaction as written would have basically this extra electron just sitting there on the product side. And we never want to have that because that implies that you're just like creating an electron, which does not happen in solution. Therefore, we need to look at, we make the half reactions and we balance the flow between them. So how we can do that is we take this second reaction where there's only the 1 electron going in, and we multiply all of the coefficients by 2 to make it 2 electrons that are flowing in. So we can think that there are 2 electrons that come out of the oxidation process and 2 electrons that go in to the reduction process. Those, when we add it together, 2 electrons cancel each other out. And we get an overall charge. So what this is really kind of showing is that the 2 electrons leave the copper and both go towards reducing different silver atoms. We can check that our overall charge is balanced. The 2 times 1 from both silver cations matches the +2 from the single copper cation. So we kind of want to get an image of this overall balanced reaction. What does this mean? It means that when a copper atom oxidizes, it's going to lose 2 electrons. And each of those electrons needs to go to 1 silver, right? Because each silver cation only is going to take exactly 1 electron. That's the chemistry of the silver half of this process, whereas the chemistry of the copper half is to release 2. And so as a result, the stoichiometry between atoms has to be 1 copper for every 2 silvers. Okay? And so what we're not going to expect to see is that copper is never going to lose 1 electron, because that's not part of the copper half process. And electrons are not just going to float freely in solution. You need to have these atoms coming in contact with each other and exchanging these electrons. So overall, we're going to have a process for balancing these redox reactions. I'm not going to go through it right here because we're going to look at a number of examples across multiple videos on how to do this. So let's get started. Balance the following reaction where F2 is reduced to F- and Cr is oxidized to Cr3+. Here is the overall reaction. Let's take a look. So we want to balance this reaction where F2 is reduced to F- and Cr is oxidized to Cr3+. So when we're working through this process, the first step is always going to be identify the half reaction, which is basically just going to be basically pairing up what reactant goes with what product. Basically, the fluorine atoms are going to turn into fluorine, and the chromium is going to turn into chromium. You're looking for the individual kind of atoms, how they are changing over the course, or types of atoms, elements, how they're changing over the course of the reaction. So that means we're going to have F2 becoming F-, and we're going to have Cr becoming Cr3+. And these are kind of the order, or the kind of our start of where we want to begin. Is peel off those 2 half reactions. From that, the first step is going to be balancing the atom. So balancing that we've done, previously, that we learned how to do. I got 1 chromium atom and 1 chromium atom. That's balanced. Here, this is 2 fluorine atoms in a molecule. This is 1 fluoride atom. So ion, sorry. So that needs a 2 in front of it. So we do want to balance atoms first, because basically the 1 fluorine molecule becomes 2 fluoride ions. So now we have our atoms balanced. Now we want to balance the charge of each of those reactions. So here I have fluorine as a reactant, and then 2 fluorides. So if I kind of want to look at my charge, well, that's neutral. And then here I have 2 times -1 for -2. So this side is 0, this side is -2. I only can balance charge by adding electrons. So I can see that basically what side is more positive, add electrons to that. So in this case, it'd be the reactant side. So it needs to be 2 electrons plus. So then I can see for charge balancing, this would be 2 times -1 plus this 0, which would be the same as this -2. Over here, chromium becomes Cr3+. This side would be 0. This side would be +3. So again, we look for the most positive side and we add electrons there, because we only can add negative charge. So if we added electrons to this 0, it would just make it more negative. Instead, we want to balance out this positive charge and add 3 electrons. So that would be 3 times -1. That would cancel out, right? It's basically just a chromium atom losing the electrons to become a cation. So those would be balanced. One of the things we can do for this particular problem is we can stop right here, and we can see that if we look at the prompt, it said that F2 was reduced. That is gain of electrons. So that means it gained electrons, which means they should be a reactant. Similarly, if chromium is oxidized, electrons as a product, right? So here you have the electrons as a product, here you have the electrons as a reactant. So that's good, because we were saying the prompt tells us that F2 is reduced. So we would think that this needs to be on the reactant side, which is, that looks good. Everything looks like we're on the right track. So we have our half reactions, we've balanced the atoms, we've balanced the charge. Now we want to combine them back together. And so what we want to do, how we want to combine them is based off these numbers of electrons. This is my oxidation process, right? So there's 3 electrons coming out of here. And then this says I have 2 electrons going in. Okay, that's not balanced, 3 and 2, so I can't just add these together. So what I need to do is basically multiply by the common multiple. And so what I'm going to do is basically take that 2, multiply it by this. So it's going to be 2 times the chromium becomes Cr3 plus 3 electrons. F2 becomes F minus. So we're basically just going to take that 3, put it in. 6 electrons plus 3 F2. Oh, excuse me, I forgot to get the 2. Don't want to forget that. Becomes 6 F minus. And then over here, we'd have 2 chromium become 2 Cr3 plus 6 electrons. So now I can see those electrons line up. Those are the same thing. So what I can do is I can add all of this together. I can do 2 chromium becomes 2 chromium 3 plus 6 electrons. 6 electrons plus 3 F2 becomes 6 F minus. And then we're going to add these together, how we've added reactions before. I have the 6 electrons plus 2 chromium plus 3 F2 becomes the 2 chromiums plus the 6 fluorides plus the 6 electrons. Cancels, right? And that's the whole idea. That's why we did this balancing. And so my overall balanced reaction is going to be 2 chromiums plus my 3 fluorines becomes 2 Cr3 plus 6 minus. 6F minus. Fluoride's tough. And so at the end, we always want to make sure, are my atoms balanced? 2 chromiums, 2 chromiums. 3 times 2 is 6 fluorines, 6 fluorines. So this is neutral, 0 charge. I'm going to write out our charge. This is 0 charge, 0 charge. 2 times 3 plus 6 times -1. Well, that'd be positive 6 and minus 6. So those are cancel each other out to give you 0, matching the 0 over here. So our atom types are balanced, our charge is balanced. This is a balanced redox reaction. So it is a little more complicated than just balancing the atoms, but it's overall always going to be this process. Identify your half reactions, balance them for atoms, balance them for charge, each one, then combine them to match up the number of electrons, then adding those together to give you your overall balanced reaction. Participation 331, question 1. Obtain the overall reaction composed of the following unbalanced half reactions. It's Al solid becomes Al3 plus aqueous, and then Au3 plus aqueous becomes Au plus aqueous. This is the first question on participation 331 due Tuesday, March 31st at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, obtain the overall reaction composed of the following unbalanced half reactions. It's aluminum solid becoming aluminum cations, and then gold 3 cations becoming gold 1 cations. Okay, we got our first question for participation 331. We are also halfway through this set of videos. So only a couple of videos left. I'm guessing we might find some more participation questions in the back half. I'll see you there.